Hello and welcome to the AbsInt Videocast for the April release in 2023. My name is Christian Himbert, and as usual it's my pleasure to provide you the latest features of our binary level analyzers in this release for AIT, StackAnalyzer, TimeWeaver, ValueAnalyzer and the TimingProfiler. The first step of all binary level analysis is the so-called decoding phase. In this phase, we need to completely reconstruct the call and control flow of the underlying task or interrupt service routine on an analysis. Before this release, it was a prerequisite to have a statically linked executable. Now, with the April release, we are introducing support for dynamically linked ELF executables for the target architectures ARM, PowerPC, RISC-V, and x86. Let's have a small demo to show you how this looks like. So in my demo application, I'm using the well-known TriStone benchmark program. It uses, among others, functions to string copy or I think also to string compare something. And in this variant of the benchmark, I've just outsourced the string copy, the string compare, and the memcopy function, well, into a module called str.c. And then later on, so I'm going to show you that, I've outsourced that or generated a separate library for the string module. It's called libstr.so. And this library has been linked against my TriStone ELF binary. All right. Okay, now let's try to analyze that piece of code, that TriStone benchmark. I'm starting with the main function, and I've just provided the ELF binary as an input. And you will see what happens if I now start to analyze it. Well, the analyzer recognizes that this ELF has not been statically linked. It contains relocations and obviously dynamic link information. And we will see, if we have a look to the graph, that somehow here in proc 0, when we call the first time the string copy x, well, the analyzer is not able to decode that string copy function because it doesn't find it in the ELF binary, right? So now it's the time to enable the support for the dynamic linked libraries. And to do so, you go to Setup, Decoding, and you can enable the option now, the dynamic linking. Well, this will not be sufficient because you also need to provide, of course, the code, which is contained in the library, right? So go to the files as well here and add another input file, namely our libstro, right? So where is it? It's here. And restart the analysis. Okay, the warnings about the dynamically linked binary disappear. We have some other warnings for relocation symbols which were not found, but these symbols are not relevant for the decoding, so we can ignore them by now. More interestingly, if we reload the graph, we will now see that, well, these calls to string copy and also to string compare and to memcopy, they are all now resolved properly so that the stack can be computed correctly since all functions or all code has been found, right? Well, one note about these addresses we have seen here, the base addresses in the input field for the executables, as soon as you enable the dynamic linking support, you might also be able to provide base addresses. In case of StackAnalyzer and TimingProfiler, this is typically not required because the analyzer or the decoder uses some virtually introduced addresses. But for the TimeWeaver, the WCET analysis, it might be required to adjust the base address here correctly so that the addresses match the addresses from the trace input as well. As usual, we have some updates in the graphical user interface. I'd like to show you that the project compare feature has been improved. It is now aware of configurations in your project. Furthermore, we can now visualize and show analysis IDs which are affected because of some AIS specification changes. And last but not least, we have some small update in the dependency editor dialog I'm going to show. Also, there are some new very helpful features in the interactive value analysis, like the visualization or the coloring of code locations that change register or memory cell contents with some respect. And you can now also query some contents of constant variables out of the symbols view if some interactive value analysis is running. Well, I'm going through all these features and give you some demo on it. At some point in your verification project, you might have two different versions of your analysis project file in which you use, for instance, the same binary, but you will get different results when you perform the analysis. So I have here scenarios project V1 and V2, and to show you the compare feature, I'd like to run both of them, and we will see we obviously get some differences here in the timing, the worst case execution timing of the 1 millisecond task over two projects. Now I could use this compare features to get more details on where this difference might come from. So here on a project level, I see, well, at least we are using the same ELF binary as a reference, so there's no difference. But let's check with the compare feature where this difference might come from. For that, I would suggest to first save a workspace for every project with the extension APSet. So we generate it here as well. And then use the compare feature here. It overrides the input, the APSet here as an input, the first input, and the APSet version 2 as a second input. And then you can click on compare, and you will get a list of results for each analysis item. And of course, we see here again that our 1 millisecond task differs. Well, this compare feature has now been improved because it also supports configurations. And we will see that in these projects, we have the default configuration, and we have separate configurations for core 0, core 1, and core 2. So obviously in both projects, the configurations are the same. But if we go to each individual analysis, we see a difference here for the 1 millisecond task. And the difference shows us that, well, for the 1 millisecond task in version 1 APSet, the core 0 configuration has been used, while in the next version, we have mapped the 1 millisecond task to core 1. And this obviously made some difference, right? So maybe we check the difference between core 0 and core 1 configuration again. Well, in the core 0 configuration, we see that, yeah, the instruction cache here has been, or the bypass has been disabled. That means in core 1, on core 1, the cache is used, instruction cache, while on core 0 it was not used. Right? And, well, this can, of course, explain the difference in the predicted worst case execution timing. No? Well, I'm sure you all know the problem. I am here in a project with several analysis items, and I'm investigating on one specific, interrupt service routine or task. And I'm changing some annotation for that analysis item. Like, for instance, here I'm reducing the recursion bound and the recursion limit from 4 down to 2. Then I'm rerunning the analysis. So this was the previous result, and if I rerun it, then I see the effect. It works here. But now you're maybe wondering what other analysis items are also affected by this change in the AS file. And this could not be answered that easily before this release. So for instance, if this annotation we have changed was even included in some local AS file, like in this case here, it's really not that obvious if an analysis here is affected. And introducing with this release, we can now call out of the AS file where we've done the modifications, the so-called Select Affected Analysis button here. If you click on that, the GUI will automatically search over all analysis items in all local, global AS files, in all included AS files, if the analysis item is affected by this change or not. And if I click here, I directly see, well, all these 4 analyses, namely the 1 millisecond task here as well, the interrupt storage routine 1, which we've known already, but also for the AIT WCET analysis types, of course. And since they are pre-selected here in this overview, I can easily do a right mouse click on it and say start analysis, and then only those which are affected can be reanalyzed. And I don't need to run the entire project, which can save time. The next update is a small one, but also quite helpful one. It is with respect to the dependency editor. You know, our 1 millisecond task is depending on our initialization analysis in it VA. And you can see that by clicking on the dependency editor here. It lists all analysis items from which this 1 millisecond task is depending on. And in this case, it's just that one initialization VA. But with this new release, we're introducing the other direction as well in the dependency editor. If you go to init VA and click on the dependency editor, you can also see a list of analysis items which use these initialization as dependency. So it lists the dependence of this analysis as well. The next new feature is for the interactive value analysis. Assume the following scenario. You are here in a loop and you open the interactive value analysis view at a certain instruction, and you are interested in a write access or read access of a pointer variable. In this case, it's a counter variable. And well, you see here in the memory cell domain that we have a certain value for that counter variable, which was here in this instruction changed from 010D to 110 hexadecimal. But obviously in the second iteration and all others of the very same loop, this information gets lost in the memory cell domain. And now you would like to investigate on why this value gets lost. So what you had to do before this release, well, you had to check manually in the basic blocks to find out where this value gets lost in the data flow. Search here again. Well, it's still there in the first iteration. Well, maybe you use some divide and conquer approach. You go to some basic blocks later. Check here again, and so on. It was kind of a boring work to find out that location where it's finally lost. Now with this release, we introduce a new feature that colors program locations where the value of registers in memory cells have changed. So let's start here above again. We can go to our value analysis domain again, search for our variable, and use the context menu to say find changes on our memory cell. Then it asks us to look for if the value has changed to some other values, to some other value which we had before, or we can also search for locations where it suddenly equals to top, which means the unknown value. So in our scenario, I would like to follow this. So we click here to equal to top, and then we look in our graph where the color changes. And well, obviously after the call to proc1, here we are losing somehow the content of that memory cell. And it's already in the very first instruction, but since this is not a store instruction, it means somewhere in the call graph, the subgraph of proc1, our value gets lost. So, okay, let's dive down to proc1 and let's repeat what we have done before. Search again for our variable. It's still known at the beginning. Find changes equal to top and look for where this value gets lost. Oh, well, obviously in the call of the memcopy this happens, and this here is because the memcopy was excluded from the analysis. So there is a not analyzed annotation, and the not analyzed has the consequence that we have to invalidate all the collected data flow information. So we found the reason why our counter variable information was lost, and we found it quite in a convenient way, in a convenient and fast way, because of this new feature to color code locations with where the values of the registered memory cells have changed. Next update affects the symbol view here and the information symbols. You typically have constant variables in your binary, and before this release it wasn't possible to directly get the contents of constant variables. So you find here, for instance, the message handler table. It's constant and it starts at this address. So if you want to see the content of that message handler table, you previously had to copy that address, go to the sections table, go here, enter the address, and say I'd like to see, well, number of bytes from that address. And I see here the first 8 bytes are zeros, and then we have some other addresses here. Now it's a bit more convenient. You can directly query the contents of constant variables from within the symbol table. For that, you, however, need to have at least one interactive value analysis running. So for instance, we could run our init VR analysis here, then we go back to the symbols view, and this needs to be opened in the background. Now we can do a right mouse click on our address, and we have a new entry in our context menu. It's called Query Contents of Message Handler Table. It asks us to select the interactive analysis to use, which is the init VA. And then, since we selected an array, a constant array here, it also asks us to select the bound. So that element of the array which we are interested in. So the very first one was 0. Well, let's go to the next element, and if we click on OK, then, well, it lists us directly in the symbols view here, the content of our constant variable. The next update I'd like to present is about TimeWeaver, more specific to the full system TraceVisualizer component of TimeWeaver. Here you can now focus much easier to specific events in the output of the TraceVisualizer, and you can better distinct between the begin and the end trace line for each task instance. Let's have a look to that TimeWeaver. I've loaded our standard example for the TimeWeaver for Tricore. It also comes with a TraceVisualizer item, and in this trace visualization item, we would like to extract all function calls and visualize, well, the order in which all these functions and tasks and interrupts are called in our execution trace. So we can just simply click to play. Then the trace is being processed, and well, the order, the execution trace is visualized, as you know, in this nice visualization and tabular overview. And well, first of all, the colors has changed here. We basically only show the blue color for the cumulative timings anymore. And what you directly see is when you mouse over a function or task, you have more details on the the begin cycles, or in terms of timing information, begin time, the end and cycle and time, but also the self-contribution compared to the cumulative contribution. So you, for instance, see that the 5 millisecond task function entry does not really contribute much to the overall timing here, just 74 cycles. But cumulative, we have 18,404 in this instance. This is basically coming from the math function, VEC, MPI, and the MAC here. So you better see the begin and the end timings in this new version. What you also can do is you can now double click to a component you would like to get more input here, more information. You can double click on this string compare and it focuses directly. It zooms in. You can zoom out with the mouse wheel if you want, and switch to others which you would like to see in more detail. And what is also good is that it is synchronized between the table and the visualization here. So whenever I click to a specific instance of my functions here for my 10 millisecond task, for instance this one, then it synchronizes also the table above, and I see the information about the begin and timings, self and cumulative contributions. I'd like to conclude today's videocast with an update on our AIS2 specification language. First of all, we now support a reference to results from computations of result combinations in AIS2 specifications. And we introduce a new functor called concat to simply construct your own symbol names, your own strings. Let's have a demo on the results of result combination computations first. Here I have now prepared a stack analysis for our 10 millisecond task. If I run that, then you see that the 10 millisecond task obviously has a system call inside of it, and the system call is triggered by proc6, maybe to change some privilege level or something like this. So usually one could embed the system call handler, the trap handler code into that graph here and rerun the analysis. But now I would like to follow the scenario where I analyze the trap handler, the system call handler separately. And I would also like to assume that this trap handler code might even be interrupted by some interrupt service routine. So for that, I have two additional analysis here. I have a separate analysis for the trap handler code and for my interrupt service routine. And I have a result combination where I'm combining the stack usage result for the trap handler and the one for the interrupt service routine, plus some context change. Okay, and now if I run this one here, I see that the combination ends up with 224 bytes of worst case stack consumption here. And this is the result I'd like to embed here instead of the 0, which is obviously not correct. So, well, for that, I could, of course, simply say, okay, I'd like to say here not analyzed. I'm going to the AIS file. I'm pasting it here. So put a try in front of it. I can uncomment the base calling conventions, and I'm uncommenting the stack consumption, and I put the 224 bytes here, right? If I rerun, then, well, the result will obviously be correct. We have 376 now in total, and we are assuming here the result from 224 from the total trap. But it would be much nicer, of course, to dynamically take the result of that result combination here. And this has become now possible in the new release. You can go there, instead of the 22 bytes, you can say, I'd like to take the result from my result combination, from the total trap combination, and in order to take effect to connect those two analysis, I need also, of course, to have a dependency, but this is automatically introduced by using this context menu entry insert result. Yeah? And if I now rerun the analysis, you see the effect here is the very same. But if I change here, for instance, some component, maybe I'm adding another 100 bytes, you see if I rerun the analysis here and say no, because it has to redo the analysis, then my result is adapted here. So you can connect with other result combination results now from AIS annotations. We have been asked by many customers for the next feature. It's having a new AIS functor called concat for string concatenation. So you can basically construct your own symbol names, your own strings in AIS now. So here in the example, you see how it works. So assume you would like to have several symbols, symbolic representations for your interrupt service routines. They all start at a given, you have a base address and a given offset for the number of your interrupt service routine. So assume so before of this release, you had to generate all these different 256 labels. Now you can generate these symbols inside of a for label, a for loop in AIS2. And for that, you just simply use that concat functor, where you have the first argument, which is a constant string, the prefix basically of your symbol, and the suffix is then the loop counter, actually, you're looping through, right? And well, the address can of course also be constructed here by this mathematical expression. So this makes the specification of such interrupt service routine labels much easier, much more compact. This concludes the presentation of the latest features and updates of our April release for this year. Thank you very much for your interest. As usual, you'll find a complete list of changes on our website. Thank you again, and goodbye.